Hi everyone, this is Kiranmay from H&S department. Today in this session we are going to discuss about optical fiber features. One of them is acceptance angle, numerical aperture and some numericals dependent on this acceptance angle and numerical aperture. So what is an acceptance angle actually? So before going for the acceptance angle, what was the principle that an optical fiber, on which principle that an optical fiber can work perfectly? That is total internal reflection. So to have total internal reflection of all the signals which has been entered into an optical fiber, it should satisfy certain conditions called as refractive index of core material should be greater than refractive index of cladding material, and also the angle of incidence at the interface between core to cladding should be greater than critical angle. If these two conditions has been satisfied, then the signal will definitely get reflected back into the core medium and it can be transmitted from one position to another position very easily due to total internal reflection. So the light launched inside the core through its one end to the other end due to total internal reflection at the core cladding interface. So to have this, light should be launched in such an angle so that it can go for uh, total internal reflection inside the core material. So when we launch a light beam into the fiber at its end, the rays which make the angle of incidence greater than critical angle at the core cladding interface undergo total internal reflection and propagate through the core. So the other rays will be losted. So we have to launch the beam of light signals at its end to enable the entire light to pass through the core. The maximum angle of launch for which the condition for the angle of incidence greater than critical angle at the interface of the core to cladding is satisfied. Such a maximum angle of incidence is called as acceptance angle. To derive it, let us consider one accept. To derive that acceptance angle, we should consider an optical fiber which is having a core and cladding. So when this acceptance angle is rotated along the axis of the cable, then a shape called conical shape will be formed around that axis of the cable. That conical shape is called as acceptance cone. If the acceptance ray is rotated around the axis of the cable, it describes a conical surface. That surface is called as acceptance cone. So let us derive an expression for acceptance angle, which can be derived by considering an optical fiber having a core material of refractive index N1 and cladding material of refractive index N2. Since core is a denser medium, N1 should be greater than N2. These are the conditions what we are supposed to take. And the surroundings for this optical fiber cable be a medium of refractive index N0, and the ray from where we are supposed to give the signal into the optical fiber, that end is called as launching end. So let us launch our signal or a light ray into the optical fiber with an angle of incidence theta I, so that the light, if this theta I is called as acceptance angle, then the angle of incidence at the core cladding will be obviously greater than or equal to critical angle, so that the light stay within the fiber. So on the screen you can observe a light signal which is incident with an angle of theta I at the launching zone. This angle got refracted into the medium because this will be a rarer, this one will be a denser medium. So the ray will bend towards the normal and it will get incident on the interface between core to cladding. Now at this point, if the angle of incidence is, that is phi, greater than or equal to critical angle, then obviously the ray will get back into the same core medium and it will get transmitted from one end to other end. For that, the conditions what we had taken here is let theta I be the incident angle and theta r be the refracted angle from outer medium to the core, and this angle refracted ray will get incident on the surface between core to cladding if this angle of incidence at this core to cladding is greater than or equal to critical angle, so obviously the ray will get back into the medium. So these are the conditions what they had taken for the derivation of an expression for acceptance angle. So now they are applying let us apply Snell's law to the incident ray, the ray which is traveling from outer medium into the core. So the here the first medium will be the launching end, and the second medium will be the core. So first medium refractive index n naught and core refractive index n1. So applying Snell's law to this one. So Snell's law is nothing but sin I by sin R. So is that is equal to n2 by n1. That is refractive index of second medium to refractive index of first medium. So let us substitute the same thing in the formula. So theta I is the incident angle, theta R is the refracted angle, and n1 is the refractive index of second medium, that is core, n0 is the refractive index of the first medium, that is surrounding medium. So sin theta I by sin theta R is equal to n1 by n0. And from figure, you can observe that theta r is nothing but 90 minus 5. If you take a triangle BCA, see here in this triangle BCA, this is a right angle triangle. So sum of the angles of this triangle will be equal to 180. So theta r plus phi plus 90 will be equal to 180. So that theta r is equal to, if you take phi and 90 on the other side, just rearrangements will give you theta r is equal to 90 minus phi. Theta r is equal to 90 minus phi. Just substituting the same thing in the formula, sin theta r is equal to sin 90 minus phi. Sin 90 minus phi is nothing but cos phi. So sin theta r is equal to cos phi. Just replacing this cos sin theta r with cos phi in the above formula, you'll have sin theta is equal to n1 by n naught into cos phi. Just keeping that aside, now apply think that the angle of incidence theta I is the maximum angle for which inside the core material at the interface phi will be equal to critical angle. Then if you replace the term, sin theta I maximum is equal to n1 by n naught cos theta c. Now just apply phi equal to theta c, then the refraction angle will be definitely 90 degrees, because if the angle of incidence is equal to critical angle, then refracted angle will be 90 degrees. So applying Snell's law for the ray, refracted ray, sin theta c by sin 90 is equal to n2 by n1, which is like incident angle is critical angle, refracted angle is 90 degrees, and the second medium is cladding, first medium is core. So n2 by n1. So sin theta c, sin 90 is 1. So sin theta c is equal to n2 by n1. As we know that there's a one formula like sin square theta plus cos square theta is equal to 1. From that, due to rearrangements, you can write cos theta c is equal to root of 1 minus sin square theta c. Just substitute in place of sin n2 by n1, and doing rearrangements, you'll get cos theta c is equal to square root of n1 square minus n2 square by n1 square. So sin theta I maximum is equal to n1 by n naught into cos theta c value, that is n1 square by n2 square by n1 square under root. Now if you get this n1 square out of the square root, that will become n1, n1 cancel. So left off with square root of n1 square minus n2 square whole divided by n naught. Just theta I maximum, that is acceptance angle, is equal to sine inverse of square root n1 square minus n2 square by n naught. This is the formula for acceptance angle. Now the next property of the optical fiber cable, that is numerical aperture, which can be defined as the light gathering capacity or light gathering ability of an optical fiber. So it can be defined mathematically as sine inverse of sine of acceptance angle, sine of acceptance angle. So NA is equal to sine theta naught, that is equal to sine of sine inverse of the angle. So sine inverse will get cancelled out. So left off with numerical aperture, that is square root of n1 square minus n2 square by n naught. Now, if you want to convert the same numerical aperture in terms of fractional difference, let us take theta is equal to, that is that will give you fractional difference between the refractive index of core material to cladding material, that is n1 minus n2 by n1. Just multiplying and dividing this term with n1 plus n2 by n1 plus n2, that will give you n1 square minus n2 square by n1 into 2n1. Now, just rearranging the terms, you will get a term n1 square minus n2 square is equal to 2n1 square delta. So numerical aperture formula is nothing but square root of n1 square minus n2 square. So if you apply square root for this one, this will be like n1 into square root 2 delta by n naught. This is the formula for numerical aperture in terms of fractional difference. In terms of fractional difference. So if the launching medium, instead of having any other medium, if the launching medium is air medium, then its refractive index will be equal to 1. Then you can change your acceptance angle as sine inverse of n1 square minus n2 square, and numerical aperture as n1 square root 2 delta, and numerical aperture is equal to, in terms of a refractive index of core and cladding, as square root of n1 square minus n2 square. So let us see one numerical based on this numerical aperture formula, where they had given you the refractive index of core and cladding material, and the light is launched from the air medium. That means the surrounding medium is air, that is n naught is equal to 1, and they are asking you to find out the numerical aperture with a formula NA is equal to square root of n1 square minus n2 square. Just substituting the above formulas, the above values in the formula, you'll get the value for numerical aperture. Let's go for the another example. That is, a glass fiber has like another example with they had given you the refractive index of core and cladding materials, and surrounding medium is air medium. And they were asking you to find out the critical angle. So they had given n1, n2, and n0 values. To find out the critical angle, the formula is sine theta c is equal to n2 by n1. Just rearranging the terms, theta c is equal to sine inverse of n2 by n1. As we know, n2 and n1 values, substituting that in the formula, you'll get an angle, critical angle, that is about 78.5. Thank you.